Okay, I'll start by thanking the organizers for putting together such a wonderful event and for the invitation to speak here. The title of my talk is RG-guided diffusion models. So yeah, so I was trained as a physicist and I've been paid by the math department in recent years. So that's my background. And my hope is that no matter how big or small the overlap between your background is with mine, you should be able to get something out of this talk, hopefully. If I'm not achieving that goal or for whatever reason, if you have any question, please just interrupt me. Okay, so the clicker is not working. Okay. Huh? Okay, it works now. So the outline of my talk is that I'll give a very brief introduction on diffusion models. It will be really, really brief just to set the stage, especially after the nice lectures this morning. And second, I'll give an equally brief, if not briefer, introduction on what renormalization group flows are. And I'm sure you'll hear more about it today after my talk. And in the third, I'll talk about what it means, what is it that we're trying to do, what's RG-guided diffusion models. So this is based on work in progress with my student Matis Gerdes, who's sitting here in the audience, and feel free to bother him. And Max Velling, and so it's an Amsterdam-based team. So the goal of this work is to try to understand and streamline and hopefully to improve some of the design choices of diffusion models using some intuitions from RG flows. Okay, so first part, as I said, we've seen a wonderful talk this morning, so I'll be super uber brief. So we have heard that diffusion models are subset of what's called generative models. And so the basic idea, how I think about it, is you have some architecture with some parameters, and after training, your parameters are fixed. You can start to generate content, and no matter it could be music, it could be images, and or field configurations. I was told that this Ising model configuration looks like a QR code, so I mean, we can try to scan it. I don't know, or make a website. Anyways, so we have heard that it has caught a lot of recent attention, and there's a lot of applications, day-to-day applications. And so the idea is very simple. It's just a quick recap. The first step is that we gradually replace, for instance, an image, which I denote phi 0 means time 0 with noise. So at the final time, the step big T, which I would call it time T equals 1, it just has become, white noise in this case. So if you do this for all data points in your data set, and so what you get is a map of distributions. So you get from the left-hand side data distribution to the right-hand side just some Gaussian, featureless Gaussian distribution. And I'll refer to this distribution as the prior distribution. The reason is once you start generating, that will be the prior where you sample from. Okay, and then the second step is that we learn the reverse process. We have heard a lot about it this morning, so I won't say much about it. And then the third step, as I said, is that once you learn the reverse process, you could just sample from the prior distribution and then do the inverse reverse flow, and then that will become the generated examples of fake cats and so on that you saw on the previous slide. So in a little bit of detail, just like the talk this morning, I will describe the diffusion process as a discretized version of stochastic process that's described by a stochastic differential equation. And then I will focus on for those of you who know, I'll focus on the variance preserving type that's given by this differential equation. So a bit of explanation, as we have seen, this the second term on the right denotes your Wiener process. And then this beta of t, which is a function of time, I take my time to be STE in the period of t equals 0 and t equals 1. And that will control how fast or how slow you noise your signal. So I'll call it the noise schedule. Okay, this will play a very important role in this talk. Okay, so that's the first part in the equation. And then, well, to see this more clearly, you can also rephrase this STE and this integrated term, integrated form. So at time t, okay, t is somewhere between 0 and 1. So the signal will look like, you know, some damping factor of t, which is between 0 and 1, which is given by the exponential of this, okay, of the integrated. Okay, the same problem as yesterday. I hope you can hear me. So this damping factor will be given by the exponential of the integration of the noising schedule. Okay, so when t becomes larger and larger, this damping factor becomes smaller and smaller. So the content, if you want, the non-noise content in your signal becomes smaller and smaller until, right, when alpha becomes 0, okay, then you don't see this original data at all. All you see is noise, okay? So epsilon is drawn from this featureless Gaussian distribution. So that's the noising process. Okay, so this SDE has an inverse SDE that's given by this. Okay, so that seems to be very nice, but the problem, of course, is that we don't know this crucial term that drives us to, you know, the data distribution. We don't know this. This is called the score, and we don't know this term because we don't know the data distribution if you want. So what we do is we throw a neural network at it, usually in a unit, to learn it. Okay. So there are different ways of phrasing it, the score matching or denoising and so on. But in essence, it can be thought of as learning the conditional distribution. So given the data here, so the noised version of data, how can you predict the less noisy version? Okay. Okay, once you have learned that, then you just sample, as I said. So here's some nice illustration. Some of you might have seen this little movie before. So you have a non-trivial distribution as your data distribution. Once you noise it, at the end, you just have like the Gaussian distribution. So now let's play the inverse movie. So that's the opposite, right? You draw a sample from this featureless distribution, and then it will give you something meaningful at the end of the process. So, right. So that's wonderful, and in practice, as we have seen, it has been very successful. However, it's not exactly, you know, a cheap procedure. So why are the costs high? Because we have to battle 3 sources of errors. The first type of errors is the error in reaching the prior. What do I mean by that? Okay, so let's look at it. Let's illustrate this with this slide, for instance. So if your noising is not complete, okay, if you have not run this long enough, then your alpha is not exactly 0. So you have residual sort of information here. So however, you thought that you have noised everything, so you still use this use this distribution as the prior distribution in the generation process. So that's a mismatch between what you do and what theory tells you to do. So that's a source of error. Okay, so coming back to the second source of error, that's the the error in learning the score. So of course, learning score is the heart and soul of this procedure. And then so it could be harder to learn, it could be easier to learn depending on, you know, how your data looks like. And the third is the discretization error. Namely, we have described this procedure in terms of a continuous process given by the SDE. However, in practice, you cut it into discrete steps, and then using, for instance, the Euler-Yama procedure, and that introduces errors. Okay, so that's my sort of lightning review of diffusion models. Are there any questions before I go to the RG flow? Okay, awesome. I think you've been hearing so much about diffusion models this today already. So what's RG flows? Not all of you are physicists. So if you want to skip this part, and then I'd like you to remember two things from RG flow, two features. One is information erasure of the irrelevant degrees of freedom, and the second one is universality. So these two things. So now explanation about the first thing. So the reason why we can do physics at all is really because there's a fact that's a separation of scales. Namely, if you want to study, let's say, the behavior of molecules, it doesn't require you to, understand the full details of string theory, right? Because I mean, they describe physics of different scales. Okay, so that's the idea. So, so suppose I start with, let's say, some theory that's very contains all kinds of, high energy degrees of freedom, which I don't care about. What do I do? So RG, I mean here by this RG, I mean like Wilsonian RG, is a scheme, roughly speaking, that erases sort of the short distance information that I don't care about while retaining the relevant long distance information at the length scale that I do care about. So that's the, erasure procedure aspects of this RG flow. So an example, what's called the real space RG by Kadanoff and Wilson, starting with Kadanoff and Wilson. So for instance, in this picture, you could see a procedure that maps, a 2x2 blocks of spin into one spin. Okay, and you could do that repeatedly, and that's what people do in condensed matter oftentimes to study the property of matter. Okay, so this map is determined by the transition function, okay, from this more, refined degrees of freedom to the rough degrees of freedom. So this transitional kernel can be given by all kinds of functions depending on your problem. For instance, in the spin context, we oftentimes people use spin decimation, for instance, in 1D Ising, or the majority rule, for instance, in 2D Ising, and so on and so forth. And in the average, in the continuous setup, for instance, if you have 5 to the 4th on the lattice, you can do some kind of average procedure when you go from that picture to this picture. But in essence, what we're doing, starting with the finer grid, is that we split our degrees of freedom into the high energy degrees of freedom and the low energy degrees of freedom, and then we retain the low energy degrees of freedom and put it on the coarser lattice, and then we throw out the high degrees of freedom. Okay, so that's the information erasure aspect of RG. And then for those of you who like field theories, let's take an example of a scalar field, and let's discuss what's called the Polchinski RG scheme. So a scalar field, is a function on, if your space-time has d dimensions, okay, then r to the d. And then you care about what you care about in Euclidean space-time is that you care about Boltzmann distribution that's given by the so-called action. And here I put the lambda here because in this Wilsonian point of view, all actions or theories or all distributions that have like an expiration date, if you want, that's given by the energy scale lambda. So this distribution is agnostic about what's going on above that energy scale. So I only care about physics below that energy scale. So the Wilsonian, the Polchinski RG is a scheme that could that tells you how the distribution changes if you lower this energy cutoff. Okay, so it's realized, for instance, in this form. So you write down the kinetic term. So phi tilde is the Fourier transform of my original field phi, and then I insert this cutoff kernel, okay, in the kinetic term, and this cutoff kernel is some function yet to be specified that determines the RG scheme, but it needs to have the feature that it sets the scale such that when the momentum is much larger than your cutoff scale lambda, then this kernel goes to 0. So it effectively it just kills, you know, the high energy degrees of freedom. This is what it does. Okay, so it's this in this way in field theory, we're also eliminating the high energy mode that's higher and then the cutoff energy scale, which is sets the scale that you care about. Okay, so that's the first aspect of RG, that it erases information at high energy that you don't care about. And the second aspect, what does it mean? Universality. Well, universality certainly plays an important role in physics. So thanks to universality, right? Like we don't need to know about all gory details of what's going on at very high energy in order to understand low energy physics. So that's some property of the flow. So which says that families of theory, for instance here T1, T2, T3, with different short distance physics, they can be very different. But as long as they're in the same basin of an attractor, they flow under RG flow to the same long distance effective theory. So that's the point with a red cross here. So that is why, you know, like for instance, critical exponents of some very different physical systems are actually the same. Okay, that's thanks to the universality property. Okay, that's I think all I want to say about RG. So just a comment. So is that diffusion is now somewhat like RG. I don't claim that this is a dictionary. Rather, I would like to think about it as an analogy. Okay, so here I'm eliminating degrees of freedom from high to low energy, high to no frequency. Okay, same thing. And then here I'm also erasing information by adding noise to the picture. Okay, and here we have some kind of universality. Namely, I could start with very different S, you know, at high energy, and under RG flow, it goes to the same fixed point action. So this is also somewhat similar. Namely, you could have a picture of cat, a picture of dog, but at the end of the flow, all you see is noise. Okay, so that's the analogy. Yeah.
In your diffusion model, you end up with a Gaussian, but as you well know, with RG, you can end up with not just a Gaussian, but you can have a non-trivial fixed point.
Yeah.
Do you imagine that you could have diffusion models with non-trivial fixed points?
Yeah, I will partially answer this question. Yeah.
Good.
Only partially though. Okay. Any more questions? Okay. So now let's come to the sort of non-review part, or not just review part of the talk, RG-guided diffusion model. So we're motivated by, you know, questions that also have been raised in the talks this morning. Namely, okay, diffusion model is described by the simple SDE, but the question is, how did we get this? What's the quote unquote derivation? And why does it work, right? And then why does it not work? Or rather, you know, it's expensive, it's not perfect, right? Can it work better? Okay, and also what's highlighted this morning is that it's diffusion model was first tested on, for instance, predominantly image tasks, but we also want to apply it to other tasks, in particular, for instance, scientific tasks. So for which class of problems does it work? I mean, do we know that a priori? Or does it work for all problems? Okay, so there are many questions, and we're motivated by also the analogy. If diffusion is somewhat like RG, what would RG say about these questions? Okay, so if you decide that you have enough of today, then maybe just summarize the rest of the talk for you in the slide before you go to bed. What we'll do is that, well, your question, right? why is the prior always homogeneous Gaussian? Okay. So we will think about this question and partially address it. And that will lead us to advocate sort of like you need to choose your data representation properly before you start doing your RG flow. And the second thing is, as we have also heard in this workshop, what we want is freedom, right? So we want more freedom. So we will also advocate that we should choose, we should generalize this a little bit. Well, or actually a lot. We should choose channel-dependent noising schedule. And then we will explain what the reason is that we should do that. And by incorporating these choices, then we have a unifying framework, or partially unifying. There are so many things out there for different diffusion schemes, that some of the different diffusion schemes that people talk about. And we also would like to offer some guidelines for these choices that one can make. Okay, so that's what I'll do in the remainder of the talk. So is there any urgent question?
Can you give some intuition for the channel dependent noise schedule? Is there like a quick RG bullet point to take away?
Yeah, exactly. Because I mean, in RG, you noise things in order, right? First high energy, and then less high energy, and then go on and so forth. So that's the cartoon intuition.
So different degrees of freedom with different masses, or like different channels that are getting activated at different times.
Yeah.
Thanks.
So, okay, so to answer this question, let's go back to the very general form of the SDE. So from here, this general form to this form that people always write down, there's a big difference. So let's talk about what happens between those. Okay, so first, we'd like to start to make some assumptions and specializations. So the first thing is that the drift should be proportional to phi. Okay, and the reason is that so we get some if we take the average, then we'll get some kind of a linear map, right? So because we want sort of your signal to, well, the non-noise content of the signal to be, linearly related with the original signal in some way. Okay, and the second is that they're dependent on t, but there's no manifest, there's no external, let's say, phi dependent. So it just says that every image, or you can replace it by your data point, gets noise in the same manner. Okay, so we don't want explicit phi dependence in this thing. Okay, in the two matrices F and G. So once you plug into these two assumptions, you get a slightly less general SDE that looks like this. Okay, so now let's take this form and look at now what are choices one has to make in order to get to the original SDE, diffusion model SDE that people write down. So the choice is that, okay, so so both AF and G are proportional to the identity matrix, and it's multiplying by a scalar. That's your noising schedule beta. Okay, so now can we justify these choices? In particular, these choices, once you write down these choices as I derived for you earlier, the prior distribution are going to be homogeneous Gaussian. So is that justified? So we think, not really. Well, why should we always be stuck with this? Okay, so let's go back to the kind of image task people usually talk about. Okay, so that's our proposal. It shouldn't be always be given by the white noise. So let's take the image task and look at the natural image data set. And the natural image data sets, they have some, pretty salient and important properties. Well, they're all approximate to qualitative, but that serves the purpose here. First, we have scale invariance, right? That means that if we look at the power spectrum roughly goes like 1 over k squared. So, so there's approximate scale invariance. If the process is Gaussian, it is stationary Gaussian, then that translates into the covariance. So the covariance in the Gaussian model of images is diagonal, and the magnitude is proportional to 1 over k squared, where k is the frequency. Right? So these are all like very well-known facts about natural image statistics. So this is to be contrasted with the covariance matrix of our prior distribution. It's just identity. It's in particular independent of frequency. So, okay, there's a mismatch between the covariance that you start with, the covariance structure you start with, and the covariance structure that you end with.
I wouldn't have thought images are scale invariant just intuitively, because when I look at stuff, you sort of, things are different scales, right?
Yeah,
yeah. So how does that, how?
Yeah, so it's not literally scale invariant. I mean, it's, first of all, it's an ensemble average, and second, we're only looking at the 2-point correlations, right? This structure tells you nothing about higher point correlations. So I'm not saying like this is free theory noise, right? So I'm not saying that natural images are noise, but it does have this structure. Yeah.
Interesting.
Yeah, it's very interesting, and also, not just images that have this approximate scale invariance. We know that many processes in nature all have this approximate scale invariance, which is very cool. Yeah. Yeah, and that also makes this discussion sort of relevant for a variety of tasks. So, well, what we propose, let me not to justify too much right now, what we propose is that we want to, instead of having a diffusion process that changes your covariance structure, we want to stay, quote unquote, in distribution. Namely, we want to have a diffusion process that keeps the covariance structure invariant, T independent. Okay, that will force us to change the kind of noise that we use, right? So instead of white noise, we need to use color noise. So we need to use noise whose covariance, whose variance have this frequency dependence. Okay. So that's a proposal, and then and for physicists, that just means that we replace the white noise spectrum with the spectrum of free scalar field theory in 2 dimensions, okay, without mass. And this is how it looks like visually, right? So this is a noising schedule with the usual diffusion prior and with, let's say, frequency dependent noise prior. So I don't know, I mean, so that's very nice. I don't know if you guys listen to noise. Well, that's something I really like listening to. You can, go on YouTube or Spotify or whatever, and then some people love listening to white noise, and some people love listening to pink noise and brown noise, and there's all kinds of debates about it. And my personal preference is the brown noise. That sounds the best. But anyways, I don't know why I'm telling you this, but this is, well, this is the brown noise, but I mean, but instead of the spatial domain in the time domain, right? In terms of sounding, right? So, but that's the brown noise is noise with 1 over k squared spectrum. 1 over k squared power spectrum. Yeah. So homework, go home and choose your favorite noise to kind of long noise to listen to. Okay, so what am I going to tell you about? So what's next? Hmm? Well, yeah, that's interesting, right? Image is 2 dimensions, and then free theory is conformal in 2 dimensions. Yeah. Well, in other dimensions, it's not. Okay, so we need to move away from noise. So that's what we propose, and then, well, it's a trivial mathematical fact, but it's still interesting to point out that choosing prior is equivalent to choosing a data representation. So what I mean is that instead of doing this diffusion, you could do this, right? You could do a change of variables, right? You can do a Fourier transform followed by frequency dependent scaling, right? And then you do the usual diffusion with the usual white noise prior. That's the same mathematically, okay? So we could reframe the question about which prior to use into the question of which data representation you use to do the diffusion. So, okay, that all sounds very fun, but so this is what I said, okay? The next part, we're going to choose data representation to do diffusion in. That all sounds very fun, but maybe I should be a little bit, before I move on, okay? I'll go back to that, the choice of data representation. So it's not just fun and seemingly nice that motivates us to make this proposal. There are some like actual computational gain that we have in the back of our mind. So this is the theorem. So in this nice paper, and so it says the following: assuming Gaussian data, there's a generalization to other kind of data distribution, but let's look at Gaussian data. And the larger the conditional number is, then the larger the discretization error is for a number of steps. Okay. So that just means the conditional number is the ratio between largest and smallest eigenvalue. And once you have normalized your variance matrix. So that just says that the more you have to change your covariance structure, the more discretization error you make. Okay, that makes sense. So and to illustrate that, we could look at just Gaussian, artificial Gaussian data that you make, and then you plot the KL divergence, between the real distribution, data distribution that's in blue, okay, and the data distribution you got after doing the reverse SDE, okay, given some steps, a number of steps of discretization. And so this is the right thing, the left thing, sorry. The left thing is with the free theory noise or the colored noise, and the right thing is with white noise. So in other words, the left thing is a diffusion process that preserves the covariance throughout, and the right thing is that one that doesn't, which is the one that people usually do. Okay, so that gives some sort of motivation. Okay, so now let's go back. So, okay, I claim that they're the same. Okay, so we could rephrase the prior question into the data representation question. Namely, what we can do instead of changing the prior, which might be easier, and more uniform, is that first we have data, and then we choose a way to represent the data that are called chi, and then we do the usual diffusion. And then, in generation process, we just do one step back to transform from chi to phi as data. as generated data, sorry. Okay, so we want to change, so we will focus on linear transformations, M, okay? In the literature, especially in the image processing literature, people also talk about more general data transformation, but we stick with linear for now. And so what should the M be? Okay, so we propose that is a choice you have to make in applying diffusion model to your problem. And then our proposal, okay, we have like a proposal for how you could choose this data representation. So in general, so to generalize that free theory thing, noise that we talked about. So in general, we claim that what you can do is you can do a PCA to decorrelate your covariance structure, so that to take your covariance structure into a diagonal form. So this is given by the orthogonal matrix U, okay? And then you do what's called whitening in image processing. So namely, you whiten your signal such that so lambda is now a diagonal matrix, right? And then you rescale your signal such that the eigenvalues of the covariance will be just all one, okay? And then so this is a transformation that uniformizes the covariance. Okay, so if you have a data set and you want to do diffusion, and you might think about, oh, Miranda said you could do this first. Okay, so that's the idea, and this is what I showed you as a justification. So that's the first part about what we want to say now today about the diffusion models. And any question before I go to the second part? Yeah. Here. Oh yeah. So whitening. It's you mean this word? Okay. So yeah. So that is this step. Okay. This rescaling step. Yeah. Exactly. Yeah. Exactly. Yeah. Thank you for the question. I'm sure. Yeah. That was a little bit back and forth. Not exactly easy to follow.
The free theory prize are drawn from a massless free theory, and I'm just wondering what that means in this context and what would change if you consider a mass term there and there would be an associated mass scale on the basis of choice of M.
Yeah, so I mean, naturally, for instance, if you have image data, it comes with kind of a mass, which is given by 1 over L, something proportional to L. L is your, for instance, L is 256. Yeah.
I see. So it's implicit in the problem.
Yeah. So, but if you do this PCA thing, then you should just read that information off.
Yeah, makes sense. Okay, thanks.
Yeah, you don't put it in. Sorry? Yeah. That's right. In this case, yes. And if you have such a data with an M, then the PCA will tell you that. Here.
Right, so the natural image power spectrum is not exactly scale invariant, as you said. So if you add those correction terms to a prior, do they actually improve the performance even more, or you kind of saturate them already?
That's a very good question. They're different, and we indeed have taken image data sets and quantify how different they are. But I think our implementation is not fine-tuned enough to see, But I hope in a month we could tell you, but according to the theory, PCA should do better than just this approximation, especially, right? I mean, natural image has also orientation. It's not exactly 1 over k-squared. There's some isotropic information there. So all that is brushed over, but will be reflected in the PCA. Okay, so I'll go to the next thing. the next thing is, okay, so now we go back to this general, but not the most general, because we have made some choices. The general SD. So how do we choose then these two matrices F and G? And we propose that the diffusion should be diagonal, okay? Should be decoupled in our chosen data representation. It shouldn't be diagonal in the original data representation, let's say images, pixels, and so on. But it should be diagonal in the, in the chi space once we have done the whitening and the PCA. So the reason, well, for instance, I mean, we already have decorrelated the covariance and the final covariance, because now it is in the chi space, it is white noise, so it's also decorrelated. So we could just keep it decorrelated. So then, in terms of equation, it just says that when chi is given by m times phi, as we said before, then both F and G should be diagonalized by the same matrix M. Okay, so here are some equations. That just means what it means. And we also want to, so it's captured by diagonal matrices. And we also want it to still be variance preserving. And so there's this relation between the drift and the noise term. So then putting things together, we get to this version of the diffusion SD that we will work with. Okay, so a few comments. So compared to the usual diffusion, which is this equation in gray, this SD in gray, there are two main differences that we're proposing. The first is that it's a different basis in which diffusion is diagonal, okay, and uniform in terms of the prior distribution. So, and there are related by this transformation, which we recommend you could try PCA and whitening. And the second thing is we decoupled the noise schedule. So now the noise schedule can be different for a different channel. Okay, we have, instead of one function beta of t, we have n function where n is, for instance, the number of pixels. Okay, so that's this proposal. And then another comment I like to make is actually about this term variance preserving. Okay, so usually people call this diffusion variance preserving, but it's really an abuse of the word, because mathematically we're not preserving the variance. As I said, the beginning variance and the final variance are just different. It's variance preserving in the sense like if one is finite, the other one is finite. But right now, once we have, if you chose your chi in the way that we recommended, then it's really variance preserving, because the covariance matrix will be identity from beginning towards the end. Okay, that's just an anecdote. That's just a digression, but I think it's important if you're familiar with the literature. Okay, so that's what I said here. So in terms of generation process, what we propose is that you have a prior that is, again, given by the white noise. And then we do the inverse diffusion. We learn the score in the usual way. And then once we have done the inverse diffusion, and then we do this data transformation too. And that will become your, So for instance, in the free theory noise, I said, this is basically Fourier space and then the real space. Okay, plus for whitening. So that's the idea. So now, okay, I've given you freedom, right? A lot of betas to choose from. So how do I think about these freedom? So what does it mean that this noise schedule could be different for a different channel? Okay, so it means that, sorry for the noise. It means that we're erasing different modes or different channels at a different time, right? That's what it means. And this is, of course, very reminiscent to RG. Well, what RG does in this regard is two things. One is it gives you an ordering. A natural ordering in RG is from high to low energy. And second is this ordering is actually used in the elimination process. So there's a hierarchy. You eliminate one mode first, and then before you go to the second. For instance, this kernel, this RG kernel can be really sharp cutoff, or it could be smooth cutoff, but it follows that pattern. So in terms of choosing the betas, what we want to know is what's the analog of high energy. Okay, when the PCA is not equal to Fourier transformation. PCA is whatever it is that your data set dictates. So we say that, okay, let's look at the variance, okay? And then the variance matrix is diagonal in this data representation. And we said that the ones with larger variance, they represent the coarse features. So they are the low energy degrees of freedom in the RG analogy. And then with a smaller variance, these are the fine details. So we want to noise these first and then noise those later, okay? In terms of generation, of course, we want to generate the coarse features first, right? And then generate the details later. Otherwise, the conditional will be absurd, right? And in particular, not easy to learn. Okay, so that's why, okay, we can also, again, look at this same SDE in the integrated form with, again, the damping factor alpha I. Now it's, channel dependent. And then we want to design, in view of time, I'll be rushing, okay? So we want to alpha I's to satisfy some conditions that, basically boils down in English, just you noise the fine details first, where I define fine details in terms of the size of the covariance earlier. So for instance, this is, I draw it according to rainbow color, so hopefully you know what it means. So this will be one example. Okay, in particular, this will be one example where the noising procedure is strictly hierarchical, right? You noise one mode out before you noise the other one. Okay, that's an extreme case, but you can have something in between, and there are many freedoms to choose these that all satisfy the idea of that, you wipe out fine details first. Okay, so this is the analogy, and you could justify it according to the Fokker-Planck equation for the distribution. On the right-hand side, RG side, this distribution is the Boltzmann distribution. Okay, and moreover, it's very nice because using sort of a VAE-inspired laws, these betas are actually open to learning. You could just learn your noise schedule. Okay, I'm concluding now. So, okay, a few things. The design choice of diffusion models can be streamlined and better understood. I think everyone agrees with that, and there are different efforts in doing also this using other points of view, which I have no time to review. I apologize. And then second is that we point out that there's an analogy between diffusion and RG, and then partially inspired by the analogy, we contribute by proposing that you first choose a data representation as the diagonal basis, and then we have some recommendation of what you could try to do. And the second is channel-dependent hierarchical noising schedule. And then combining this, well, you actually get a unifying sort of framework to describe some of these different very nice diffusion methods, trying to make diffusion models faster and cheaper. So for instance, in this paper, they use the wavelet basis, and here's the famous sort of cascading. So you can think about it as, choosing a data representation that's basically the real space, right? So you just coarse grain it and then and then non-overlapping noising schedule. So you generate one thing at a time. So you could try to understand those. In this framework also gives you more knobs to tune, okay, or more parameters to learn. So there are 3 sources of error, and then we talked about discretization error, and the hierarchical structure will hopefully make the score learning easier. And then the error in reaching the prior, that's, well, we just have to make sure that we noise everything sufficiently. So that's some attempts to understand and improve diffusion model. So here, thank you.
Very much. We're a little over time, but we have time for 1 or 2 questions. Yep.
So I have a quick question on analogy. So during the RG flow, there can be things which are invariants like global symmetries or anomalies. Is there a similar analog in a diffusion model also, or it can't be built like that?
Yeah, I haven't thought too much about it, but I mean, we should check. Yeah. I mean, so far it's just an analogy, but I mean, it's still interesting to push the analogy. Yeah.
Since we have to minimize number of questions, I'll combine 2 in 1. So have you done experiments? And related to that, it sounds like diagonalization is extremely costly procedure in practice in terms of implementation. So any advice or techniques to assist PCA in doing that?
The first question is yes. I mean, I can show you some videos, but they're preliminary. We're still tuning things up, and also we're trying to analyze the data so we could quantify the performance better, other than just eye inspection. And then about doing PCA, is that the question? Diagonalization. Okay. Yeah, so far that hasn't been the bottleneck, but indeed that's interesting to think about. I don't have much to say, but we can talk about that later. I mean, there's many techniques in doing those, and yeah.
One last question from a diffusion expert.
Thanks, and thanks for the great talk. I really like the renormalization group approach to that. I have a fairly practical question. At the end of the day, you need to learn a denoiser, right? A big neural network that denoises everything. And now if you move away from pixel space, for instance, are you also proposing to use like different architectures, for instance? You know, these typical convnets that you use, they just work really good on images. And yeah, so this is kind of one worry I would have. That
Yeah. That's a great question.
New architectures now.
Yeah, that's a great question. So in reality, we still use the UNet. I mean, we just, we choose 2 bases according to what we want to do. And then for learning, we still use the original basis and then use the UNet. Yeah.
I see, that makes sense. Yeah. Thanks.
All right, I will save my question for the break, Miranda. So let's thank Miranda one more time for the beautiful talk.